Alright, so we're going to continue with 13.8, and in our last video we covered relative max and relative min values. So now we're going to talk about absolute max and absolute min values. So to find absolute maximum and minimum values of a continuous function function f on a closed bounded set R in the plane. So 1, find the values of f at all critical points of f in R. 2, find the extreme values of f on the boundary of R. And 3, the largest values from steps 1 and 2. The largest value, not value, those things. So the largest value from steps 1 and 2 is the absolute max. The smallest value from steps 1 and 2, or the smallest value from steps 1 and 2 is the absolute minimum. All right, so similar to what we did in Calculus 1, you would find critical points in your closed interval in Calculus 1, and then after that, you would check, evaluate your function at the endpoints of your interval as well, and then you compare all the values. So we're doing the same thing here, it's just instead of having an interval, we just have some region R in the XY plane. So we're going to do an example. Now this is not an example that's in your textbook. So it's not an exercise from the textbook. So example, find the absolute max / min values of f of x, y equals 2x cubed plus y to the fourth on the set R equals the set of points xy such that x squared plus y squared is less than or equal to 1. So I'll use this. We'll see this notation a lot for when we start talking about domains. I mean, when we talked about domains, we saw, and we'll see it a lot later in the course, where this is just the set of points x, y that satisfy this equation or this inequality. So it's any x, y such that x squared plus y squared is less than or equal to 1. All right, so now this problem, although it's not in your textbook, this is like problems 25 through 28 on page 882. So this is like page 882, numbers 25 through 28. All right, so now what we're going to do is we're going to go through these 3 steps here to find the absolute max and min. So first, step 1, we have to find the critical points that are in this region. And actually, let's just sketch the region over here. So our region is just a disk in the xy plane, standing at the origin with radius 1. So, and it includes the boundary, which is this circle, and then all the points inside of there as well. All right, so that's our region R. So we have to find the critical points that are in this region. So what we do is we just go about finding the critical points of this function as usual, and then we keep anything that's in this region. If it's not in that region, we don't need to consider it at all. So to find our critical points, we'll take the partial of f with respect to x. And when we do that, we get 6x squared. And the partial of f with respect to y equals 4y cubed. So we need these both to be equal to 0 simultaneously. So we have 6x squared equals 0, 4y cubed equals 0. And so this tells us x equals 0. This tells us y equals 0. Notice here there's no restriction on what y is. So as long as x is 0, y can be anything, and this will be 0. As long as y is 0, x can be anything, and this can be 0. But we need them both to be 0, so we only get the point 0, comma 0, which is indeed in this region. All right, so our critical point is in there. So I'm just going to put a little box around, or a little circle or something around this point, because I need to evaluate my function at that point, and I don't want to forget about it. So as soon as I find a point at which I need to evaluate the function, I go ahead and evaluate the function there. So maybe I just put it off here to the margin so I remember to look back at it. So f of 0, 0, what do we get when we do that? We just get 0 there. All right, so that's one of our comparison values for step 3 is going to be 0. All right, now step 2 says find the extreme values of f on the boundary of R. So now we need to find the max and min values on the boundary, which is this circle. So now usually you end up having to break your boundary up into multiple functions. So here, this top half of the circle will be y equals the square root of 1 minus x squared. And down here, the bottom half will be y equals negative square root of 1 minus x squared. So you would break your boundary up into as many separate functions as necessary. So here we would have 2 separate functions. And then what you do is you take this boundary function and you substitute it back into here for y. So now instead of f of x, just any y, it's going to be f of x comma the square root of 1 minus x squared. And we'll put that in and we'll put that in. then this thing becomes a function of one variable, just of x. And we know how to find max and min values for a function of one variable. So that's the approach. And then after we did that, this would be our boundary one. We would do our boundary two. Take that, put it in right here as well. And then when we put that in, we now have a function of one variable, and we will find the max and min values for that. So on this region, that would be your usual approach. But notice for us, when we put in y here, it's going to get raised to the fourth. We put in this y, it's going to get raised to the fourth. So these two y's, when we put them in, they're going to give us the exact same thing because of that. So instead of looking at the top and the bottom of the circle separately, we can just look at y squared, which will give us the whole circle. So our boundary, usually for this, you would have a boundary one, you would do the steps I'm going to do, and a boundary two, and you would do the steps I'm going to do. So our boundary, though, we can handle it in one swoop just because this is being raised to the fourth power. So our boundary is just going to be y squared equals 1 minus x squared. Now, why didn't I leave it as x squared plus y squared equals 1? Because I want to be able to substitute into here. And I see that this has a y squared in it. So I will solve the boundary equation for y squared. And now I'm just going to put that in there. So now we have f of x comma, instead of putting in y, we're going to replace this right here. This is y squared squared. So we're just going to call it f of, I just say f of y, f of x comma 1 minus x squared equals 2x cubed minus, that's x cubed right there, minus, we're taking this and putting it in there. So this is y squared. So notice this is y squared squared. So we're not going to raise this to the fourth. We're going to just square this. So it should be 1 minus x squared squared. Right? Because this is y squared right there inside the parentheses. And then the square right there means that we still have y to the fourth, which is what we should have, 2x cubed minus y to the fourth. That's what our function says. Now this is a function of one variable. It's just a function of x. So we're going to call that g of x. So now with g of x, we need to make sure we consider the domain because we're trying to find the absolute max and min values. So what is the domain for this? Now, right here. So to ensure that we remain on that boundary for this circle, what can our x values vary between? If we look at this, our x varies between -1 and 1. So that's how we figure out our bounds, and that's an important aspect because now we are back in calculus 1 with a function of one variable on a closed bounded interval, and we're doing extreme values of that. So now we're going to take the derivative of g, set it equal to 0, solve for x, put in those critical points to see what we get, and we're also going to put in the endpoints to see what we get there as well. All right, so g prime of x, g prime of x is going to give us 6x squared minus 2 times 1 minus x squared raised to the first power times a negative 2x, the derivative of the inside. So put that plus right there and a positive 2x right there. All right, so we're going to simplify this, set it equal to 0, and solve for x. So this is equal to 6x squared minus 4x. Oh, no, not minus, plus 4x. And then minus the 2x cubed, 4x cubed, excuse me. All right, I have all my signs correct before I start going to town on this. I do. Oh, wait a minute. I do have all my signs correct, with the exception of that somehow got changed to a minus sign. I don't know how that happened. The way I looked. All right, so that was supposed to be a plus sign. I don't know what happened there. Oh, I think maybe I was looking at that minus sign right there. I don't know how that happened. That should have been a plus sign, which now what does that do? That changes. That should be a negative right there then. So this is, I'm going to put the negative 2x right there since I have a plus right there. And now that changes this to a positive 4x cubed. And this is a negative. So we're going to put plus a negative 4x. Sorry about that. All right, so now we have 4x cubed plus 6x squared minus 4x. We're going to set this equal to 0 and solve for x. So we'll say 4x cubed plus 6x squared minus 4x equals 0. And we can factor out a 2x from this, or divide both sides by 2x. When we do that, well, actually, let's factor out a 2x so we don't forget. So 2x times 2x squared plus 3x minus 2 equals 0. So this tells us that x equals 0, or this quantity in parentheses equals 0. So I'm going to go to the next page, so make sure we all have that down. Let me double check, make sure all this is correct. 4x cubed, 6x squared minus 4x, 2x, 3x, and 2. Okay. And we can't forget about our endpoints either, so we'll address those on the next page. All right, so we get 2x equals 0, or 2x squared plus 3x minus 2 equals 0. So this gives us x equals 0, and this is going to give us x equals negative 3 plus or minus the square root of 9 minus 4 times 2 times negative 2, negative 4. All over 4. So we get this equals negative 3 plus or minus. Here we get 9 plus 16, which gives us 25, and the square root of 25 is 5 over 4. So we get 2 points here. We get negative 3 plus the 5, which gives us 2 over 4. So we get 1/2. And then we get negative 3 minus the 5 gives us negative 8 over 4, gives us negative 2. All right, so we got x equals 0, x equals 1/2, x equals negative 2. But remember, our domain is x has to be between negative 1 and 1. So we're not concerned with that negative 2. So we need to take these values and put them back into our function g to see which ones are going to give us the largest values. And remember, we're really concerned with the function f, but let's go back to actually, I'll just write it down here. So we're concerned with the function f, but remember, g of x is f of x comma 1 minus x squared. So g is our function f still. So we haven't lost this function f, which was 2x cubed plus 1 minus x squared quantity squared. So now we need to do g of 0, and we need to do g of 1/2. We already have, which is, for us, when we do g of 0, that's the same as f of 0 comma 1. And when we do g of 1/2, that's the same as f of 1/2 comma 3/4. So G of 0 is going to give us 0 here, and then we're going to get 1 right here. And then G of, what do we have? G of 1/2. G of 1/2. Actually, I should have put these in the margin. So the G of 0 is f of 0, 1, which is 1. So I'm putting all our comparison values over in the margin. And then G of 1/2, when we put that in, we're going to get 2 over 8. And then 1 minus, what am I putting in? 1/2. So 1 minus 1/2 squared, which gives us 3/4. And then that square gives us 9 over 16. So plus 9 over 16. So we get 4 plus 9 over 16, which is 13 over 16. And that is f of 1/2, 3/4 is 13 over 16. Now, what we can't forget about are the endpoints of our interval from -1 to 1. So that is G of 1. When we do G of 1, we're going to get 2. And then we're just going to get 0 over there. So we're just going to get 2. And G of 1 is the same as if we put in 1 here and 1 right there. It's the same as f of 1, 0. So f of 1, 0 is 2. And then G of -1. We put in -1 here. We're going to get 2 times -1 gives us -2. And here we're just going to get 1 minus 1 again. So we're going to get 0. So we get -2. And when we put in -1, that's f of -1, 0. So f of -1, 0 gave us -2. So now we have addressed all of our values that were on the interior of that region. So the origin was our only critical point on the inside, and we got f of 0. F of 0, 0 was 0. So I'm just going to write that one over here again since it's not on this page. So now what we're going to do is we compare all of these values that we got here, and then we see what our absolute max and our absolute min are. So the smallest number that we have here is -2. So we have an absolute min of -2 at the point -1, 0. And we have an absolute max of 2 at the point 1, 0. Oops, sorry. So notice it just so happened that our absolute max and min were at those endpoints. So you have to make sure that you check those endpoints, because had we not checked those, we would have lost our correct answers entirely. All right, so we have just a few more minutes in today's lecture. So what I'll do is I'll start one more problem from the textbook, but then I'll finish it in our next lecture. So I'm going to kind of bounce back and forth a little bit between sections 13.8 and 13.9 because they're very closely related. But we've seen now the basic types of problems from 13.8, where you just use a second partials test, or you find the absolute max and min. The rest of the problems in this section and most of the problems in this section are actually application problems. So we're going to start one of those, and then I'll finish it in our next lecture. So we're going to look at number 30 on page 882. So number 30 says, in the remaining exercises in this section, assume that the required extreme values exist. So that means when you're told that when you go through a problem at the end, you don't have to use the second partials test to see is this thing a max or a min, or go through any of those steps. They're telling you from the nature of the problem, whatever you find at the end, you know that that is the answer that you saw in the beginning. So we know that the absolute max or a relative max or whatever it is that we're looking for, we know that they indeed exist. All right, so it says find three positive numbers whose product is 48 and whose sum is as small as possible. Calculate the sum. All right, so for problems like this, we're going to be given two things. We're going to be given what's called an objective and what's called a constraint. So they said find three positive numbers whose product is 48. All right, so that would be our constraint. Well, let's look at how you find your objective before I talk about the constraint. The terminology as small as possible, that's telling us what we're trying to optimize. Like, what are we trying to maximize or minimize? The as small as possible saying we're trying to minimize something. So let's look at our objective. Objective meaning like your goal. What is it they want us to minimize? They want us to minimize the sum of these three numbers. And we'll call the three numbers X, Y, and Z. And we'll just call this, S. We just need some name for it. I'm probably a little bit later, I'm probably going to end up switching gears and calling it F. But for now, we'll just call it S for sum. That's our objective. Now, we are subject to the constraint that X times Y times Z has to be equal to 48. Their product has to be 48. So your constraint is going to be that thing that you're given some numerical value for. Oftentimes you still will have to come up yourself both with the objective equation and the objective function and the constraint equation. So now what we can do is everything that we've done up to this point has been a function with functions of two variables. And now we have this function of three variables and we're trying to find max and min for it. So what you do is the same thing that we did in the past in Calculus 1 for objective constraint problems like this. You solve this for one of the variables and then you substitute in here. Now we like our functions to be functions of X and Y. You could make it a function of X and Z or Y and Z, but because we wanted this to be a function of X and Y, we're going to solve this for Z and substitute it in here. So here this tells us Z equals 48 over X times Y. And always be cognizant of dividing by variables. Make sure you're not dividing by 0. We know that X and Y, neither X nor Y could be 0 because that will make this left-hand side 0 while the right-hand side is 48. So we don't have any issue here. And now we're going to take this, substitute that in there. And now once we do that, now this will be a function of X and Y. So our objective becomes f of xy equals x plus y plus 48 over x times y. All right, so since I'm out of time for this lecture, we've gotten to the point where now we actually have a function set up. So now you all can go through the steps and find the partial of f with respect to x, the partial of f with respect to y to find your critical points. And remember, they're saying assume that your extreme values exist. So if you only find one critical point, you're done, which is what is going to happen for most of these problems. You don't have to go through and say, okay, I need to do the second partials test or anything. Once you find that single critical point, you know that has to be the max or the min or whatever it is you saw that they told you exists. All right, so you all can finish this off. I'll continue it in the next lecture, but you can try it in the meantime. And we'll continue 13.8 and then start 13.9.